Okay, all right, let's get started. Lots to do. We were talking last class about Taylor and Maclaurin Series, and I wanted to mention to you that there is a page in the book. Unfortunately, I don't want to bring up the book right now, but it's on page 484 of the book. There is a list of the common Maclaurin series. And so we did last class, I showed you that sine x was sum n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. I showed you that last class. That's in this book on this table. And there's a Maclaurin series for 1 over x, e to the x, sine x, cosine x, arc tan x, natural log of 1 plus x, and then there's even one for binomial expansion. Be aware of those. If you move on to classes that are going to use series, you are not going to be asked to derive the Maclaurin series. You're going to be referenced to some table, and then you'll go grab the Maclaurin series, all right, and then use it for whatever you need to use it for, all right? What we do in here, since this is a math class, is we try and figure out where these formulas actually come from, right? How do we generate them? All right, so be aware of those. We're going to do our first example. We're going to do a Taylor series now. The difference between Taylor series and a Maclaurin series is that A is 0 in a Maclaurin series, right? And with a Taylor series, A can be anything, right? Any number. Now, what this actually does, do you remember when I showed you, very beginning of this chapter, how we take a function and then we approximate it? And I showed you these approximations getting closer and closer and closer to the true function. That's what our series is doing. It's doing an approximation. And sometimes that approximation can only work within a certain window. That's our radius of convergence, right? So what if we're interested in what's happening to the function outside of that radius of convergence? All we have to do is shift it. The A moves the whole function left and right, so we can move our interval, our radius of convergence, our interval of convergence, to the window that we're interested in. Does that kind of make sense? I'll try and show you with a visual later on. Let's just get down to the mechanics of this. All right, so the big thing here is that our series f of x, right, the power series, can be rewritten this way. C sub n, x minus a to the n, right? And we developed the formula for this C sub n. It is the nth derivative where? At 0, that's if it's Maclaurin. At a in general, so it's going to be 2, but I'm just putting the formula up here so we can use it, over n factorial, right? So our focus is to try and figure out if we can come up with some formula or some way to get a pattern of how these constants are being generated. And to do that, we just have to keep looking at successive derivatives of the function. But this time, the derivatives are not evaluated at 0. They're evaluated, in this example, at 2. All right? So let's go ahead. Let's start. The 0th derivative of this function is what? E to the x. And it actually turns out that when you now take that 0th derivative and plug in 2, you get e squared, right? What did we get last class for the Maclaurin series? What did we keep getting over here for the Maclaurin series? 1, 1, 1, 1, 1, 1, 1. And because this is e to the x, yeah, it's always going to be, derivative's always going to be e to the x. So when we take the derivative and we plug in 2, we're going to get e squared again. And it's just going to keep happening, right? Yeah. So this is a somewhat boring Taylor series. There's not a lot going on here. This is going to keep giving us e squared no matter what, regardless of the derivative we're at. Okay? Yeah. So when we come back over here for the power series, for this particular function, it's Taylor series. None of my black markers are working very well. Let me see here. The function should be, I might have to go to blue. Let's see how my blues are. I will start throwing markers, yes.
I enjoyed that video. It was a great video.
What happened?
You were just like, hold on a second. You storm out of the room, you come back with the trash can, you're like,
oh yeah,
these are garbage.
I remember that. They were all dead. What is this right here for us going to be? That's e squared. Okay, it's never changing. It's always e squared. And then we still have over n factorial, right? And then a little bit of a change here. X minus 2 to the n. That's our Taylor series. Now we can start plugging some stuff in here. Let's just look at the first few of these guys. If we plug in n is 0, we get e squared here, right? 0 factorial is going to be 1, so we get e squared. X minus 2 to the 0, 1, right? So all we get for our first term of the series is what? E squared. E squared. Okay. Plus, now we move along. E squared over 1 factorial is just e squared again, but this time x minus 2 to the first power. So e squared times x minus 2, right? Next one, e squared over 2 factorial, which is just 2, right? I'll put 2 factorial, it's the same thing. And then x minus 2 squared, one more. E squared over 3 factorial, x minus 2 cubed. We're cubed, right? And keep going. So the idea here is that if I plug this into this function, I'm sorry, if I have a computer start graphing this polynomial, and now for the computer I'd have to stop somewhere, right? Yeah. But if I go far enough, it should get closer and closer to what this function looks like, e to the x, especially around 2. So if you graph e to the x, here's 2, right? E to the x looks like this. Then my polynomials are going to start marching towards this thing. And close to 2 means that if there is a radius of convergence, I've moved my radius of convergence over to where my polynomial will be accurate within that window. All right. Again, I'll try and show you with some visuals later. All right, that's pretty boring. We still haven't done one that actually requires a lot of, I guess, thinking. I don't know if it's a lot of thinking, but it's, I'll leave part of that up there. So let's try this one. Let's try natural log of x. Okay, so we're going to find the Taylor series for f of x equals natural log x at or about a equals 3. All right, so we're just going to start taking derivatives, right? And then plugging what into those derivatives? 3. And then try and see if we can find a pattern. All right, so we take the 0th derivative, which is just ln x itself, plug in 3 into that, and we get ln 3. It's definitely going to change, isn't it? Okay, the first derivative of this is 1 over x. And then when we plug in 3 into this, we get 1/3, don't we? Now be careful on your second derivative. Negative 1 over x squared, right? Negative 1 over x squared. So we're going to take the second derivative, we're going to plug 3 in. We should get negative 1 over 3 squared, right? which is 1/9. But I am going to write it as 3 squared just to try, yeah, I did forget the negative, just to try and pick up a pattern, all right? Because my next one should be a 3 cubed, shouldn't it? Now, will it be positive or negative?
Positive.
Positive. So, are you all okay with taking successive derivatives here? Next derivative will be positive 1 over x cubed. 2. Very important. Let me rewrite this. I had negative x to the negative 2, right?
Yeah.
And I'm taking the derivative of that. So negative 2 pops out. So this is this, right? Negative 2 pops out, becomes positive 2, x to the negative 3 drops back down. So that's going to give us the third derivative at 3 is 2 over 3 to the third.
27. Next one is -6.
So what would the next one be? I'm taking the derivative of 2x to the negative 3, right? Negative 6. Okay. Okay, so watch. Fourth derivative at x. You said negative 6?
Yeah, -6.
Okay. I agree it's negative 6. Where did the negative 6 come from?
Well, the power rule.
I'm doing 2 times negative 3, right? We all know that's negative 6. But I'm going to do negative 2 times 3 over x to the 4th. Y'all agree with that? Why am I leaving it as negative 2 times 3? What do you think?
You're trying to find that.
It's looking like it might be a factorial here. On my next derivative, well, we'll see. Let's plug in 3. I'm going to stop writing this down, okay? Is that all right if I stop writing this down? We're plugging 3 into that. So we just get negative 2 times 3 over 3 to the 4th. All right, let me continue my table here. I'm now going to be taking the derivative of that. So I have negative 2 times 3x to the negative 4, and I'm taking the derivative, right? Negative 2 times 3 is a constant. The negative 4 comes out. Positive now, right? This is all positive, but I have 2 times 3 times 4, right?
So it's a factorial.
So my next one, I'm going to continue my table here. So my fifth derivative at x should be 2 times 3 times 4. It's positive, right? Over x to the fifth power. And then when I plug in 3, I get 2 times 3 times 4 over 3 to the fifth. Do you see why things could start becoming problematic in terms of finding a pattern if you start like making this negative 6 and then leaving this as like actually figure out what 3 to the 4th is? Then you would like reduce the fractions, like cancel 3's, and you would lose the pattern that way. It would be harder to see it. Okay? That's why I just leave everything written out. Make sense? Can we predict what the next one's going to be without doing the work? Okay, negative 2 times 3 times 4 times 5 over x to the 6th. And then when we come over here, negative 2 times 3 times 4 times 5 over 3 to the 6th. And the next one should be positive 2 times 3 times 4 times 5 times 6 over 3 to the 7th. Right? So I'm curious to know then, what would the nth derivative, let's actually plug in 3. What would the nth derivative at 3 be?
Is it n minus 1 factor?
Yeah, so here's where we have to pick up the pattern.
Negative 1 to the end.
The sixth derivative gives me a negative, right?
Factorial.
The fifth derivative, positive.
N minus 1.
Fourth derivative, negative. So it looks like we're alternating, right? Positive, negative, positive, negative, positive, negative. We can take care of that. And then the numerators are always factorial, but one less than the derivative I'm taking. So n minus 1 factorial. Looks like it's on top. And then on the bottom, it's 3 raised to whatever the derivative is, right? So it looks something like this. We have n minus 1 factorial on top, and on the bottom, 3 to the n. I just haven't done the alternating yet.
Right, you should
So how can I do the alternating?
have some sort of
Negative 1, and I need all the even derivatives to be negative and all the odds to be positive. So what am I going to use there? N plus 1. So if I plug in 6 here, right? If I plug in 6 like this one, if I plug in 6, this is going to be to the 7th power. That'll give me a negative. If I plug in 5 here, this is going to be 6, and then I'll have a positive, right? Does this look good, everyone?
Do we have to start at 1 though?
Okay, so does this formula work for every single one of these? It does not work for the first one.
But it eventually does.
Yep, it does not work for this one, does it? If you try the 0th derivative, you plug 0 into this formula, you're not going to get natural log
What
3,
we can do is
right?
we can split that. We can get our split that series up.
Yeah, what we're going to do is split that out in the front, okay? Because that's the only one that fails to follow the formula, all right? We good? All right, let's try and write the series then. Okay, this function, okay, should be equal to natural log 3. That was that first piece that we could not find the formula for, right? Well, are we done with that?
I don't know. Are we?
Remember what these were. It's natural log 3 over 0 factorial x minus 3 to the 0, right? That's what that first piece should look like. Now, the 0 factorial and the x minus 3 to the 0, those are all going to become 1. So yes, our first term is natural log 3. But I want you to remember there's more to the formula that you have to address. Now, the rest of this should follow my formula. So sum n equals 1 to infinity, okay? And now, this is my formula,
We have to put in.
and we have to put this formula into the formula for C sub n. C sub n, remember, was this over n factorial. Yes? You all right? Okay, erase this. So here comes my formula, right here. Negative 1 to the n plus 1 times n minus 1 factorial over 3 to the n, but all of that over n factorial, then times x minus 3 to the n.
Really simple.
Do y'all see all this? You'll see where all those pieces come from? You see how different this is than the previous problem? Previous problem was just e squared, e squared, e squared. This piece up here was never changing, right? This time, this changes. We found the actual formula for it, and then we can just plug it into this. Now, this does simplify. So let me try and clean this up. The first term is just natural log 3 plus sum n equals 1 to infinity. And now, let me do it this way. Negative 1 to the n plus 1 times n minus 1 factorial over n factorial times 3 to the n, and then x minus 3 to the n. So I just tried to clean up this complex fraction a little bit by bringing this n factorial here. What else am I going to do? Yeah, I'm going to peel out, because I've got an n factorial and n minus 1 factorial. I'm going to break the n factorial down to n times n minus 1 factorial and cancel the n minus 1 factorials. So ln 3 plus sum n equals 1 to infinity of negative 1 to the n plus 1, sorry. And then I'm trusting that everyone can take that, and that's just going to become 1 over n. That's 1 over n? Yes? So how about we do this? Times 1 over n times 3 to the n, x minus 3 to the n. Let me double check what I've got here. Yeah, that's right. No questions? Everyone understands where the factorials went? They disappeared, yes? Okay. And that's it. This is our power series. Now what we could do is start writing out the terms. So we could go natural log 3 plus, and then start plugging in n's. And I would start at 1. So if I plug in 1, we're going to get a positive, right? Is that right? We get a positive. And then we should get 1 Plugging in 1 here and 1 here, we get 1/3 times x minus 3.